I want to show you one of my favorite pictures. This is an image of a protoplanetary system, a protostellar disk. This is a newly forming planetary system that we are seeing. This isn't an artist's illustration. This is the real thing. And if you like that, here's 10 more. More than 10 more. And this is all thanks to the Atacama Large Millimeter Array. And this is an array of telescopes in Chile that work together, viewing into the millimeter, into the submillimeter, and have just given us a peek into a type of process out there in the universe that is really important to us. Like, how did the solar system form? But not only this, ALMA has given us a view into so many other astrophysical processes happening across the universe, from the largest scales to the smallest scales. Even though we can't see the millimeter, submillimeter wavelength with our eyes, it is really important scientifically. But there are limits to what you can get with an array of relatively small telescopes, 9-meter telescopes. There's something to be said for a giant single telescope. My guest today is Dr. Claudia Cicone. She is an associate professor at the University of Oslo, and she is working on the Atacama Large Aperture Submillimeter Telescope project, AtLAST. And this is designed potentially to be the follow-on to ALMA. So in addition to this array of small 9-meter telescopes, there could be this giant 50-meter telescope sitting among them and doing a whole other kind of science still in that submillimeter millimeter array. And the possibilities are quite exciting. So enjoy this interview with Dr. Cicone. For those who aren't completely familiar with the electromagnetic spectrum, where's like the submillimeter range? What's that good for?
Okay, so the submillimeter is the frequency or the wavelength between the infrared and the radio, okay? So a bit longer wavelengths than infrared and then a bit shorter than radio. And probably people are familiar with the microwave. The microwave is actually the long wavelength part of the submillimeter range, okay? And for astrophysics, this is the wavelengths at which we can access cold material in the universe. So emission lines from rotational transitions of molecules in the universe, even water transitions, and but also the emission from the cold dust. And everything that is obscured by dust, the dust will absorb the optical ultraviolet radiation and re-emit it in the infrared and submillimeter if it's colder. So basically, in this wavelength range, we can see 50% of the energy of the light in the universe, which we cannot see at other wavelengths.
So with James Webb, you needed to go to space to be able to see that infrared light, because I guess you're getting the heat from everywhere and it doesn't go through the atmosphere very well. Why does submillimeter work for ground-based telescopes?
Yes, because contrary to the infrared and the far infrared, the submillimeter wavelengths are not completely blocked from the atmosphere. Indeed, we call them submillimeter windows. It means that there are certain chunks of frequencies, not everything continuously, but there are certain chunks of frequencies where the atmospheric absorption, so the absorption from the Earth atmosphere, is not 100%, but it could be 20%, 30%, 50%. So now the challenge in observing at these wavelengths is that, of course, being not completely transmitted by the atmosphere, we need to place our telescopes very high in altitude so that the light has to pass through fewer possible layers of the atmosphere. And indeed, what absorbs the submillimeter wavelengths is mainly the water in our atmosphere, because the water has transitions in this wavelength, okay? So even the water from our planet. So what we do, since the water is mainly in the lower part of the atmosphere, we place our telescopes a bit high, not so high because, from Earth, so we can access actually sites on at 4,000, 5,000 meters max. And there we actually managed to get a very good atmospheric transmission most of the year, which enables the observation at this particular wavelength. Okay, of course, if you could place some millimeter telescope in space, you would completely remove the problem of the atmosphere. But the problem is that being longer wavelength than the infrared, in space we cannot launch very big telescopes. We can launch smaller telescopes like JWST. And so it means that the angular resolution that you can get in space is much lower than what you can get with an interferometer or with a very large single dish on Earth. So there is this kind of trade-off between angular resolution, which is determined by the aperture, the diameter of your telescope, or the longest baseline of your interferometer, and the atmospheric transmission, the sensitivity of your telescope, which of course is the higher the better. The first submillimeter experiments actually were using balloons. Actually, even now it's used, that go in the stratosphere. Okay, so there you have actually you manage to get a very good atmospheric transmission without going into phone space.
Yeah, I know. It's amazing how much of these experiments are tested on balloon first, on suborbital rockets, and I love how like balloons are like this middle range of telescope that you can test out your idea, see if it works, and then decide go to space or maybe stay on the ground. So I want to talk about first ALMA, and then that will lead into the telescope that you're working on. So, probably most people's understanding of submillimeter astronomy is coming from ALMA. So can you describe the facility for people?
Yeah, so ALMA is an interferometer, what we call an interferometer, which is an ensemble of many antennas. Okay, in the case of ALMA, it's 66 antennas, and they observe simultaneously the same source in the sky. And what they do is to correlate the signal. Okay, so they basically through this technique, through which the signal is basically multiplied, we manage to reconstruct a signal, the signal that is common between all antennas. Okay, so all antennas are observing at the same time the sky and the source. The problem of submillimeter observations and even for ALMA, which is placed at 5,000 meters, is that the noise from the atmosphere, from the sky, is much higher than the signal that you want to observe. So you need to really be clever to extract the signal. And with interferometers, by facing these antennas, you can actually identify the signal that has exactly the same properties across all antennas, okay? And this way allows you to place antennas fairly far apart and achieve a much better angular resolution, which is basically the capability of distinguishing very small details in the sky by having, by not building a very, very large antenna. Okay. The problem is that this technique does not really observe the source. It observes what a mathematical operation on the signal, okay, the Fourier transform of your source. And then you have to reconstruct, okay, deconvolve the signal to reconstruct the morphology, the properties of your source, okay. Even the total flux, which you may think is the easiest property to get, okay, how much light am I getting, how much luminosity am I getting at this wavelength, is actually very hard to constrain with an interferometer, because the interferometer is never observing everything. And it's, in order to have a perfect interferometer, you need to have an infinite number of antennas placed at infinitesimal distances between each other. But you can't. Actually, because there is a physical limit of placing two antennas at the minimum distance, which is given by their diameter. and actually a bit higher than that, because you don't want the antenna to shadow each other. So interferometry is great in getting very fine details of sources in the sky. But first of all, it's complicated because you need to multiply the signal from this many antennas. So it's a lot of data. You have many, many antennas, and so that each antenna needs to be equipped with a receiver. So you don't need to build one instrument, you need to build 66 instruments. And then you have to process this enormous data set. You need all antennas to be working well at the same time, and sometimes these antennas are placed at kilometers distance between each other. Okay, so there could be some atmospheric instability in one antenna but not in the other. And so there are a lot of complications, and the ultimate complication is that we actually never know what the source looks like, and we have to make some assumptions to reconstruct the source from the Fourier transform of its brightness, which can be dangerous if you absolutely have no idea of what your source looks like.
I mean, partly it's this classic trade-off. When you build these interferometers, they give you a much larger, you get the larger baseline, you get better resolution, but you don't get the sensitivity. So you can only look at the brightest objects. I mean, I think people are fairly familiar, with the Event Horizon Telescope, where they were only able to look at, say, the event horizons, the shadows of the event horizons at those two objects. So is it the same thing? I mean, you're sort of stopping me for a second there. So how is that different than the situation that you're dealing with?
Actually, I wanted to correct you, because sensitivity, it's a very complicated parameter, because the sensitivity, we can describe it as how high is my signal with respect to the noise, okay? So basically, higher sensitivity means that your telescope is capable of detecting fainter signals. The problem, the advantage of interferometry is actually, by having so many antennas, the collecting areas, so the photons, the number of photons that they get from the source is actually very high. And so the sensitivity is high, but the sensitivity is concentrated in a very, very small area. Indeed, an interferometer measures the sensitivity per beam, per resolution element. And having a very, very small resolution element, which allows you to distinguish very well the details, you're placing all of your sensitivity onto this very small region. So the sensitivity is actually high, but it's high for very, very small sources. As soon as your source starts to be larger than your resolution element and larger than your area, you have to basically, your requirement goes as the square of your sensitivity of the sides of your resolution element. So as soon as the source is more extended, then you actually need the square of the sensitivity. And so your actual sensitivity on the extended signal is lower by square root, okay, of how many times is your size larger than the resolution element.
I see. So and that's why I guess the Event Horizon Telescope had the perfect target with something that's incredibly tiny and very bright, as opposed to, say, if you wanted to image some large star-forming nebula that is many degrees across in the sky, right? Exactly. I understand. Okay. So then I think you were leading to the downsides of having this interferometer. The solution is one big telescope again.
Yeah, but I want to make some justice to ALMA, in the sense that it's amazing what ALMA can achieve. And before you mentioned the protoplanetary, this level of details and this level of point source sensitivity is unprecedented. Okay, so without ALMA, we will never know how these sources look like. But exactly. The downside is that interferometry cannot do all the science. Okay, there is some science, for example, mapping very extended, very faint, diffuse nebulae, or even mapping large areas of the sky. that interferometers are not very good at. And indeed, we don't really use them to do this. What we use to do these other signs is what we call single dishes, which is basically one of the antenna, used as a standalone telescope. Now, single dish telescopes then you may ask, why don't we just pick one antenna of ALMA and use it standalone? This we are already doing, However, these antennas are quite small, 12 meters, and they are equipped with some receivers, some instruments that are quite old already, because ALMA, when you plan an interferometer, you start a project like ALMA, the planning started decades ago. And then, they used the state-of-the-art instrumentation, but by now it's already a little bit obsolete compared to what we can achieve. The problem is that when you have new instruments, you don't test them on an interferometer, because you have to build 66 version of those. You test them on single dishes. So single dishes enable to do a lot of science that interferometers cannot do and have a lot of advantages, especially if you build them with characteristics that are, state of the art. For example, a single dish, if you want to have some resolution, not as high as ALMA, but you need a larger diameter. And if you want to map large areas of the sky, you need a larger field of view. Field of view is the portion of the sky that you can observe simultaneously. For ALMA antennas, the field of view is quite small. So even when we use them as single dish, we have the problem of the relatively small diameter, the relatively small the field of view, and the relatively old instrumentation. So we have actually done almost all of that science that we could do with these specifications. Now we want the next generation.
So this led, and I reached out to your team because you're working on the design for the AtLAST telescope. So can you talk about this telescope?
Yeah, so this telescope, first of all, it doesn't exist yet. We are indeed working on a design study, so a feasibility study. The telescope, we knew more or less what we wanted in terms of technical capabilities, but we didn't have a plan, we didn't have a design. So 4 years ago, almost 5, we sent a proposal, an application to the European Commission, which funds research, a little bit of funding, gives a little bit of funding to research, but all of the research, not just astronomy. And then we got some funding to perform this feasibility study, which we are now completing. And so the AtLAST project is indeed, the attempt to design the perfect, next generation submillimeter telescope. And what makes this telescope really unique, and what actually requires us to do a 4 years feasibility study, is that this telescope combines a very large diameter, 50 meter, which is extremely large for a submillimeter telescope. It's not very large for a radio telescope, but for submillimeter, it's unprecedented, with a field of view of 2 degrees, which is as large as we can build on very small single dish telescopes, 6 meters, but it has never been built on a 50-meter telescope. And it hosts multiple instruments at the same time, up to 6. So every instrument can access this huge field of view. So you can actually, develop instrumentation for 30, 40 years, and you will still not, exhaust the possibilities offered by this telescope, because this telescope is actually preceding the instrumentation development. We don't have the expertise to build instruments that can access the full field of view. For example, in spectroscopy, we can do that in just continuum in imaging, but in spectroscopy it's still very challenging. But the deal is that to build a telescope that can be used and can host instrumentation for many decades, right? And all of this needs to be able to observe submillimeter wavelengths, which means that submillimeter from 300 microns up to 10 millimeters, okay? The challenge here is the 300 microns wavelength, because in order to observe this wavelength, you need the surface of your reflector, of your primary mirror, to be precise enough so that the wavelength actually bounce are reflected into the secondary mirror and then into the instrumentation. And in order to do that, it means that the imperfections on your surface needs to be at least a few times, several times, okay, the more the better, smaller than the minimum wavelength that you want to observe. So actually the requirement on the AtLAST surface is that the imperfections do not exceed 20 microns, which means that we should be able to observe 300, 350 micron in wavelength, which is basically far infrared, okay? It's the shortest wavelength that is not completely blocked from Earth. And this is an extremely high, it's very challenging engineering wise. So, and that's why these large dishes are built for the radio wavelength range, because you can actually even make holes in them. We have even some dishes that have a grid, because you don't need this precision and this accuracy for the radio. But for the submillimeter, it's basically crazy, because this precision is the same precision that you have on the ALMA antennas, but those are 12 meters. So you need to achieve it on a 50 meter.
Wow. That sounds that sounds really complicated. But let's say that you do achieve this. What then could be accomplished with a 50-meter single submillimeter telescope?
Yes, so I didn't finish because this was just one of the tasks of the design study, so to design the telescope. And then the other challenges is to find the best place where to build the telescope. And we concluded that there are the best places near ALMA, so that this telescope can actually collaborate with ALMA, access the same part of the sky as ALMA, and actually, incidentally, that is even one of the best sites for submillimeter observation. Actually, it's the best after the South Pole, but in the South Pole, it would be impossible to have to operate this telescope, because this telescope is not going to be a survey telescope. It's going to be a facility telescope with several instruments and people that need to access it all the time. And another part of this design study was the challenge to find a way to make the telescope powered by renewable energy, 100%. So to make the telescope completely sustainable. And this is a whole other field of research, because you need to power 3 megawatt of a telescope, which is, hundreds of times the requirement of an apartment. You need to do it constantly, night and day, 24/7 across all seasons of the year. You cannot afford power shortage, because otherwise your instrumentation warms up, because you need to keep it cool, and it's also dangerous for the people working there. So it's a very, very extreme challenge, and it's another field of research. So the design study of AtLAST actually considers all the aspects of building and operating these new facilities, not just the design of the telescope, which, by the way, we have achieved. We have now a paper out which is in peer review, where we actually, our team of engineers have actually achieved, at least on the computer, the capabilities that we want for this telescope. And part of this design study was also to study more in detail the science that is going to come out of this telescope, okay? These numbers that I told you, like 50 meter diameter, they come from science requirements, okay? They are not completely random. So these are the numbers that we understood would provide a transformational, jump into our scientific capabilities. So what science will come out of this telescope? Surveys. What is a survey? Scanning the whole sky of including the sky, the plane of our galaxy, so the molecular gas content, the dust content of our galaxy, but doing this with the sensitivity and the resolution that is unprecedented and allows you to study the connections between electromagnetic fields, so the radiation, the magnetic fields, because we can through polarization, we can study dust polarization with appropriate instrumentation, and the gas and the star formation with a resolution that is actually high enough, because we did have surveys of the Milky Way plane, right? But with very low angular resolution. But the 50 meter allows you actually to detect and identify protoplanetary disks, okay, not resolving them, but you can detect them, and you don't detect anymore, the tip of the iceberg of the population of, clouds, but actually you start to detect the typical populations of all the sources that you want to observe. And this applies also for the extragalactic science, so the study of other galaxies than our. We can by survey the whole sky in continuum and line emission. With this sensitivity, we can actually detect the typical galaxies that we are still missing and that can be observed only in the submillimeter, typical galaxies in the distant universe. On top of this, so surveys or scanning of large areas of the sky with all the possible instruments that we can conceive, the fact that this is a single dish, it means that this is going to be very good at detecting everything that is diffuse and extended. So if there is a gas in the molecular form, which emits only in the submillimeter, that is very faint and very, very extended, this telescope will detect it. And we think that there is a lot of this gas in galaxies, around the galaxies, between galaxies, that we have never detected before, and that we cannot detect, okay, so far with current instruments. Why do we think it exists? We think it exists because we start to see some little signatures with, when we use ALMA in the compact configuration in a very distant source so that we can probe a little bit larger scales, we start to see signal in places where there shouldn't be. So far from the star-forming part of the galaxies, far from the typical disks that are at the center of galaxies. But it's like if you get these small blobs that are not connected to each other and are very low signal to noise, so the scientific community, half of the scientific community doesn't really believe that, but we're getting many, many of these cases, and we are now starting to back it up with theory that says, these galaxies, they don't live in vacuum. There is material between galaxies because they interact with each other. They launch powerful winds. They accrete material from outside. So everything that is not in the center of galaxies, we are completely blind to in the submillimeter.
I know that a lot of observations have been made more recently about that, say, intergalactic gas reserves by looking at, say, quasar light as it's moving through large distances. But it's one thing to just say, yes, we detect its existence, and it's another thing to measure the location and the concentrations and where these things are and how they interact with the galaxies. And I think that's the difference, to know it's there versus exactly where it is.
Yeah, detecting it in emission, it's the problem. In absorption through the quasars, it has been done. But in absorption, you see the spectral figures, but you don't have an image. And you don't have a total luminosity. You don't have the geometry of this material. So the challenge is to detect it in emission. Now we start to have some, we're not totally crazy. We're not building a telescope because a few blobs. We have in other wavelengths the signature of this gas. For example, in Lyman alpha, which is a tracer of hydrogen, recombination of ionized hydrogen. Which you can observe in the UV, in the ultraviolet, and then at higher redshift, it gets redshifted into the optical. So now with optical telescope, we are observing this very extended, we call them Lyman alpha nebulae. But on these scales, we have no facility that can follow them up in the submillimeter. And it would be extremely interesting to constrain how much molecular gas there is in this nebula, how much dust there is in this nebula. Because unfortunately, Lyman alpha, it's not really probing the phase of the gas that is forming stars. Lyman alpha can even be illuminated by quasars from outside, and it's extremely hard to get quantities, physical constraints, only from Lyman alpha. So Lyman alpha is telling us there is a lot of gas there, but it doesn't tell us if this gas is cold, if it's dense, how much there is, what is it doing, if there is star formation there. So this is a very fascinating question, because I don't know if you seem to be expert of everything, but we are missing half of the baryons. We are missing actually most of the baryons in some galaxies. We don't know where the gas, the dust, the stars are. So we measure, the baryonic, we call baryons everything that is non-dark matter, okay? All the matter that, we can observe in some wavelength, in some way, but we're missing most of it, okay? In some special environment in galaxy clusters, we think we have a good understanding of where the baryons are. And spoiler, they are between the galaxies. But in normal galaxies, in what we call field galaxies or in groups, we don't really know where are these baryons or in what phase they are.
Right. So you're offering to find half of the matter in the universe.
Or more.
Or more. Right.
No, but okay. This is one of the goals, and maybe it's the one that is a little bit more stretched. Okay, the very low hanging fruits of AtLAST is gonna be these incredible maps of the submillimeter sky at a sensitivity and resolution that we have never had before.
That's really interesting. I mean, we think about these maps of the sky. Obviously, everyone's familiar with the cosmic microwave background radiation. I'm sure people are very familiar with the ones that have been done in infrared, where you see the Milky Way across the entire thing, visible ones. But we don't have a submillimeter view of the entire sky. And radio is one that is also very tricky to produce.
Well, we do. The Planck maps are actually in the submillimeter, but they are extremely low spatial resolution. And they are only tracing the continuum, the broadband continuum. So the emission from the matter, it has some what we call continuum component, which is basically emission, spectral emission that doesn't change much with frequency, with wavelength. So you basically take together a chunk of frequency, merge everything together, make a map. And that map is going to trace those processes that do not have quantum transitions, right? So it's not going to trace the gas. Or if there is some transition in there, it's going to be completely diluted into the signal. Planck did these all sky maps, and CMB experiments did. It's not that we don't have them. The problem is that the resolution is, extremely low. So the problem when you have like a source, a protostar or a galaxy nearby, and you have your source is very small, and then you have your resolution element that is 10, 15, 20, 30 times larger, you don't detect the source anymore, unless that source is as bright as to dominate everything that is in there. So this is called confusion. Okay, so those maps are confusion limited in the sense that the signal is so diluted into the noise or into other signals that you actually don't detect them anymore. So it's not that the information can be retrieved by some special AI analysis, that there is not there. And also the small aperture, it means that only the brightest sources will be detected. Okay, those telescopes are optimized for the CMB, for the cosmic microwave background, which produces anisotropies that are really large compared to our sources. However, and of course that they miss completely the line, which is what I'm most interested and excited about, right? The line emission from atoms and molecules in the universe, in absorption and in emission especially. But I'll tell you what, so we cannot use the CMB maps created by Planck to do much other science than that. But the CMB people are going to be really excited about the AtLAST maps, not because of the CMB, but because the AtLAST maps will constrain at unprecedented details what for them is the noise, the foreground. So everything that the universe is emitting that is in front of the CMB. And the level of precision at which they are now measuring the anisotropies of the CMB is such that they are really limited by the capability of subtracting and modeling and subtracting this foreground signal from their maps, which is dominated by our own galaxy, but actually it has all of the other galaxies in it.
So, I mean, I think about some of the other issues, like say with the Hubble tension, that you could then provide a more accurate measurement of the microwave interference, of the submillimeter interference that's coming, and then they could constrain their error bars on their measurements of the age and size of the universe, and probably make the Hubble tension more complicated. Who knows? So then, okay, so what is your timeline? So let's say that you're currently in the design phase right now, or a capability study. I'm guessing then that moves, if somebody says, yes, let's build this, then there's the design phase, then the build. When would you like to see first light on this telescope?
Okay.
Assuming everything goes great.
If everything
everything's going to go perfect. Yeah.
So if everything is great and we have funding for building it, we would be ready in a few years. Actually, we don't really need much more because all of the major challenges are already solved. Okay, so now in August is the official end of our current design study, but the results are already out. We're just addressing the peer review. Okay, but what is coming next? The next is just we would need maybe 2-3 years more to test some of the most innovative part of our design. For example, what I didn't mention is that the telescope itself is also somehow trying to be sustainable by using the technology that we use to recuperate energy in electric cars. So we are going to place supercapacitors on this huge and massive telescope. This telescope is going to be massive, okay? So most of the energy consumed by the telescope, when it accelerates, it's going to be massive and very fast. It has to accelerate very fast because this is the requirement that we placed on it. So actually, most of this energy that you consume, the power that you consume to accelerate, you can recuperate it using this technology, like you do with electric cars when you are going downhill, right? And but this somehow has never been done before. For a telescope. So this is some piece of technology that we want to test on a prototype, on an existing telescope. Then there is the big, so another thing that we should test is the metrology system. The metrology is what we call the entire technology that allows us to correct for the deformation of the telescope under its own gravity, under the solar, because in the Submillimeter we observe also during the day. So the telescope it can even point the sun, the AtLAST telescope. So, the sun can modify your material, hopefully not too much, but certainly creates some deformation. The wind deformation, you need to compensate in real time because you remember we need this 20 micron precision on the surface. And this is is achieved by a loop of sensors that are in real time detecting this deformation and sending the information into the telescope to adjust the position of the panels of the telescope. This other piece of technology, we need to test it also. And then we need to understand what instruments are we going to place on the telescope, because a telescope without instrument is useless. So we have designed the telescope, but we have placed for up to 6 instruments. So we need to decide which are going to be the first light instruments, so the first generation of instruments installed on the telescope. So there is a lot of things that require a little bit of testing, but this is going to be 2-3 years if we have the funding and we have the participation that we're having now, and then we would be completely ready to start construction, because we have the site, we have the measurements of the site, we have the plan, we have everything.
And how long do you think construction would take?
That I don't know. A few years.
Yeah,
I don't know.
But like maybe we would see it in the 2030s?
Yeah, that's if everything goes well, we could go on the sky in the early 2030s.
Right. Wow, it's fascinating. So I guess you mentioned you're in peer review now. When do you have to deliver this next design?
We actually we have to deliver everything to the European Commission by the end of August. Okay.
Right.
But most of these things we have delivered already. What I mentioned with peer review is actually, it's a bit tricky in the sense that this is the design itself is okay. It needs what is called a preliminary design review, but this is not something that the referee of the journal reading the paper is going to do. This is something that involves a team of engineers. The engineers, the people with the expertise to do this kind of review are very few in the world, and most of them are already involved in the AtLAST study. So basically, in these 3 years of time that I told you that we need 2 months to do the preliminary design review of the telescope, okay? Which is the formal engineering language to say, okay, we are ready to go on, okay? And this is also part of the activities that if we get further funding, we will do now in the next years. Now we have published the documents, the preprint of the papers are all available online already. But of course, there is a process of peer reviewing of the journals. But the documents have already been submitted and published. So we are almost done, basically. What is missing is just a few remaining reports on, for example, on the site measurements that we are still taking. So we are waiting to get as many measurements as we can so that we trace the seasonal variations of the wind of the, in 2 sites that we have selected where we have put our instrumentation. So there are a few things that we still need to do, but we are done basically.
Well, good luck with that. I look forward to these all sky images in Submillimeter. That sounds great. Thank you for your time.
Thank you.
I hope you enjoyed this interview with Dr. Claudia Cicone. Now I'm going to talk some more about sort of my thoughts on the interview, but first I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Dennis Alberti, Dougie Stewart, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Mark Anstis, Modso, Paul Rohrbach, Stephen Grasaki, Stephen Fowler-Munley, Vlad Chiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. When I give talks at astronomy conferences or various public events, one of the pictures that I lean on is that image of a protoplanetary system. When I first saw this image of actual planets orbiting an actual star, when I see the disks, the rings carved out, and the variety of these different objects, I don't know what to say. I feel this connection to sort of the history of the solar system, to see these other objects forming at different ages in the universe is mind-blowing. And it's this wavelength that we just don't have access to with our own eyeballs. And yet there's so much science that could be done. And we're just at the beginning stages of what is possible. That right now we have some of these telescope arrays, and yet we can see larger and larger instruments that can carry on and be able to give us even more understanding of the universe around us. Now, I have done plenty of interviews about large telescope projects in various wavelengths, so I'll link a couple of those here. All right, thanks a lot. We'll see you next time.